Hello everyone, I welcome you all into today's presentation. Today we intend to start a new topic, and that is design of various IC engine components. In these presentations, we would like to discuss the design procedure of cylinder, piston, connecting rod and crankshaft. Today we intend to start the same, and in today's presentation we would like to discuss design of an IC engine cylinder. At the end of this presentation, students shall be able to understand various functions of cylinder in an IC engine, the likely materials for cylinder of an IC engine, and finally design of cylinder of an IC engine that includes determination of length and bore of cylinder, thickness of cylinder wall, thickness of cylinder cover, diameter of studs and other relevant parameters. Before moving further, let us discuss what are various functions of an IC engine cylinder. We all know that the working fluid, which is air plus petrol in case of SI engine and which is air in case of diesel engine, is contained within a cylinder. So the primary function of cylinder is to retain the working fluid, such as mixture of air and petrol or air and diesel, and secondary function is to guide the piston. As you can see in these animations, here we can see that this is cylinder, this is piston, and this is connecting rod, and these are two valves. So cylinder is guiding the piston, at the same time it is retaining the working fluid. Cylinder and frame is made up of one piece casting, whereas in large engines a separate cylinder liner is used. That means the cylinder liner, water jacket and frame are manufactured separately and then they are assembled. In this diagram you can see that this is cylinder liner and this is water jacket. They are two separate parts. A cylinder liner can be of two types, dry liner and wet liner. A dry liner does not have direct contact with cooling water in the jacket. As you can see that this is water jacket and this is liner. They are not having any contact between them. Whereas in wet liner, it has its outer surface in direct contact with the cooling water in the jacket. We can see that in the diagram. This is water jacket. It is in direct contact with the cylinder liner. Now the primary advantage of cylinder liner is they are economical. Just imagine, in absence of cylinder liner, we need to take the whole cylinder of some superior material. But when we go for cylinder liner, we only need to have better grade material for the cylinder liner, and for the remaining cylinder we can have an ordinary cast iron. So instead of taking the whole material of superior quality, we can only use cylinder liner of superior quality so that when worn it can be easily replaced. Let us come on to the cylinder materials. What are the requirements of a cylinder material? As we all know that in a 4-stroke diesel engine, pressure can have as high as 35 bar. That means a cylinder material should be strong enough to withstand high gas pressure. Further, the temperature can be as high as 2000 degrees centigrade. So it should be strong enough to withstand thermal stresses. Since piston is continuously moving within the cylinder, it should be hard enough to resist wear due to piston movement. Further, it should also have good surface finish to reduce friction during piston movement, and it should be corrosion resistance. So these are few requirements that a good cylinder material should possess. What are common cylinder materials? The most common cylinder material is grey cast iron. Now the reason arises why grey cast iron usually preferred as a common cylinder material. There are few advantages with grey cast iron. The primary one is with grey cast iron, complex geometries can be easily casted. It has extremely good machinability properties. It is extremely dimensionally stable under heating, and it is high vibration damping and surface lubrication retention properties. That is why most of the cylinders are made up of grey cast iron. Nickel cast iron or nickel chromium cast iron can also be used as a cylinder material for heavy duty applications. For small engines, cast steels and aluminum alloys can also be used. So these were few common cylinder materials that are usually used. Now let us come on to the main topic, that is design of cylinders. When we talk about design of cylinder, what we are supposed to do, what we are supposed to design. This is a line diagram of a cylinder piston assembly. So basically we need to find following dimensions of a cylinder when we talk about design of cylinder. The primary one being bore of cylinder, which is here, internal diameter of cylinder. Then length of cylinder, this is length of cylinder. Then thickness of cylinder wall, this is the cylinder thickness. Thickness of cylinder head, this is cylinder head which accommodates various walls. So this thickness we need to find for a given cylinder. Then number and diameter of cylinder head studs. Usually cylinder and cylinder head are two different parts. So they are assembled together with the means of gasket and studs. So when we talk about design of cylinder, we also need to find how many studs are required, at what pitch circle diameter they are to be used, and what would be the required diameter of the stud. So design of cylinder basically involves determining all these dimensions, that is bore of cylinder, length of cylinder, thickness of cylinder wall, thickness of cylinder head, number and diameter of cylinder head studs, and pitch circle diameter of studs. Now in the upcoming slides, we would like to discuss all of these parameters one by one and how they can be assessed using design equations. Let us first discuss how to find bore and length of cylinder. We all know these are very common formulas that we have had in our previous courses. Brake power is given by PMB LAN over 60, where PMB is brake mean effective pressure, L is length of stroke, A area of cylinder, that is pi/4 d square, where D is diameter of bore which is required to be determined, N is number of working strokes. In 4-stroke engine, N will be N by 2, and for 2-stroke engine, N will be equal to N. Similarly, the IP is also given by PMLAN/60. Here PM is indicated mean effective pressure, and the ratio of these two, that is BP/IP, is given by mechanical efficiency. So how to use these formulas for determination of bore and length, that is the question. What we do, we generally have either BP or IP, and one of the pressure, either PMB or PM. Say for one case we have been given PM, that is IM, indicated mean effective pressure, BP. So how we can use that? We are usually given the mechanical efficiency, which is ratio of BP and IP. If not given, the usual value is 80%. So from the value of 80% and for the given value of BP, we'll find IP. We found IP because we have been given this PM. Now IP is known to us, PM is known to us. The only unknown remain is L and A. N is for 4-stroke engine, it will be N by 2. For 2-stroke engine, it will be N. So in L and A, the unknowns are L, length of stroke, and D, diameter of bore. Usually the ratio is 1.25 to 2. So if not given, we can take L by D as 1.5. So in a way, we have replaced L in terms of D. So there is only one unknown left, and that is D, diameter of cylinder bore. So for the given value of PM, eta M, and BP, or vice versa, if PMB is given to us and IP is given to us, we can use this formula. So in any case, we'll be ready with what will be the value of cylinder bore. For a 4-stroke diesel engine which is developing 5 kilowatt power, bore diameter could be in the range of 100 to 125 millimeters, when IMEP is 3 to 4 bar. These are usual values which gives us a vague idea that what could be the diameter of cylinder bore. Obviously, for cylinders, for engines developing more power, the diameter of bore would be definitely higher. So in this slide, we found what is. Now, in the previous slide, we found what is diameter of cylinder bore, and by the ratio of length of stroke and diameter of cylinder bore, we can also find what would be length of stroke, which is 1.5 times usually of the cylinder bore. Now, length of stroke, as we can see in this diagram, is somewhat smaller than the length of cylinder. It is usually 15% more. Length of cylinder is 15% more than the length of stroke. So if we know by the formulas that we have seen in the previous slide, what is cylinder bore? From cylinder bore and L by D ratio, we can find length of stroke, and increasing 15% length of stroke gives us length of cylinder. So by this time, we are able to find what is bore and what is length of cylinder. Now, thickness of cylinder wall. We design the cylinder wall as considering it as a thin cylinder. We know there are circumferential hoop stress and longitudinal stress, and design stress for a thin cylinder is circumferential or hoop stress. So we usually modify the formula for design of thin cylinder to make it applicable for designing cylinders of an IC engine. The formula is P max T over 2 sigma C plus C, where T is thickness of cylinder wall which is required to be found, that is in millimeters. P max is maximum gas pressure inside cylinder, that is 10 times IMEP. Sigma C is permissible circumferential or hoop stress for cylinder material. If not given, we can assume it to be some value between 35 to 100 megapascal. D is bore diameter and C is reboring allowance in millimeter. This is the reference table which can be used to find value of C, reboring allowance, according to the cylinder diameter. We must know that reboring is required to compensate uneven wear on inner walls of the cylinder. It is basically additional metal thickness required over and above that required to withstand maximum gas pressure inside the cylinder. So if this T from this formula comes out to be say 10 mm, so for a bore diameter of 100 mm, we need to put 2.4 mm as reboring allowance. So required thickness would be this thickness plus reboring allowance. This data table is readily available along with these formula also. We just need to find the procedure, understand the procedure. Otherwise, all these formulas will easily find in any of the data book. So using this formula, we can easily find what would be our thickness of cylinder wall. Next comes cylinder head. In most of the IC engines, a separate cylinder head or cylinder cover is provided. If the cylinder is small, then we don't require a cylinder head. But when the power to be developed is more, then cylinder head and cylinder are two different entities. Separate cylinder head is required because it accommodates following parts: inlet and exhaust ports, air and gas ports, spark plug in case of spark engine, and atomizer in case of diesel engine. This is a picture of a common cylinder head used for a four-cylinder engine. As we can see that calculating various dimensions of actual cylinder head is quite cumbersome. So what we do in preliminary stages, cylinder head is assumed as a flat circular plate and thickness is calculated. This is the formula which is used universally to determine thickness of cylinder head. TH is thickness of cylinder head in millimeters. D is again bore diameter. K is a constant whose value is generally 0.162. Pmax is again maximum gas pressure inside cylinder, which is 10 times IMEP. And sigma C is permissible circumferential stress for cylinder head materials. We may have same material for cylinder and cylinder head, and we may have different material also for cylinder head. The common value of sigma C for cylinder head is 30 to 50 megapascal. So if not given, we can assume some value between these two values. So by this time, we are able to find what is bore of cylinder, what is length of cylinder, what is thickness of cylinder wall, what is thickness of cylinder head. Now comes how to assemble cylinder head and cylinder. So for that we need a gasket and studs, because to make the assembly leak proof, studs are used along with gasket so that the cylinder head may not come out when the gas pressure is being imposed. So studs are used to assemble cylinder head and gasket, and that provides a leak proof joint. A preload is induced, as we know that for uh, vessels subjected to internal pressure, we always use studs or bolts, and those are preloaded bolts or preloaded studs. That a certain compressive stress is induced so that when they are encountered with actual working conditions, there is always some preload which help them retain the leak proof joint. What do we mean by design of studs? It usually includes how many studs are required, what would be diameter of studs, and what would be pitch of studs. In this slide, we would like to answer these questions, that is number of studs, diameter of studs, and pitch circle diameter of studs. So these are the ranges which help us to find number of studs. Minimum stud should be 0.01 D plus 4 and maximum studs should be 0.02 D plus 4. To give you an idea, for a 200 bore diameter cylinder, number of studs using these two values should be within 6 to 8. Next comes diameter of studs. This is found by using this formula. Pi d square by 4 into P max is the gas force, and pi d c square upon 4 into sigma T over Z into Z, this gives resisting force. This is the gas force, this is resisting force. Equating these two, we can find dc. Because we know what is d, we have already found. What is P max? 10 times IMP. Number of studs we found from here. Sigma T is permissible tensile stress for the stud material. We can found for the given material. So only unknown left is DC, which is core diameter of stud. So if sigma T is not known to us, we can easily take its value from the data book, that is 35 to 70 megapascal. So in this equation, only unknown is DC. From DC, we can find what would be the nominal diameter of stud. Now remains pitch cycle diameter of studs. dP is given by D, which is bore diameter, plus 3D. 3D. D is diameter of stud. So pitch of stud will be circumference pi dp over number of studs. Pitch should be between 18 root d to 28.5 root d. We can find pitch of studs from this formula, and we must check that our pitch should lie between these two values. So in this small presentation, we learned about how to design a cylinder for an IC engine. What are the basic dimensions which needs to be determined for the given cylinder, that is bore of cylinder, length of cylinder, thickness of cylinder wall, thickness of cylinder head, diameter of studs, number of studs, and pitch cycle diameter of stud. In our next presentation, we would like to discuss the design of piston. I think you have enjoyed this presentation. I thank you all for patient hearing.